Fortunately, I will talk in English because I invited my colleagues and also I invited
That's good.
students too. So, and my presentation will be devoted to generalized simple waves in continuum mechanics. Actually, continuum mechanics here, it is too maybe wide. I will talk only about three models, and one it is gas dynamics, one-dimensional gas dynamics, then nonlinear elastic materials, and a little bit about magneto-gas dynamics. So this, my presentation, I want to dedicate to Nikolai Nikolaevich who was advisor and also great mathematician. And we, this year, we try to organize conference in Thailand, which will be online, unfortunately, because I'm not sure that Thailand will be open at this time. And so the conference will be in August. I want to invite all participants to participate in this conference. So before starting, I want to give one example, simple example, so about methods for constructing exact solutions. Actually, all methods of constructing exact solutions, they such that it is necessary to give some assumptions, and using these assumptions after that construction of solutions will be algorithmic. So, but first assumptions and method depends on assumptions. For example, if we have group analysis, then it is admittedly group, or then we construct partial invariant solutions or invariant solutions. If you have so-called method of degenerate hadograph, in this case, there is relations between dependent variables. So here I will give example on the wave equation. So wave equation can be reduced to a system, actually for system, because I will work with system of equations, then I will show here a system of equations. It is very well known D'Alembert solution of these systems, and it is easier to demonstrate. So, for example, in group analysis, we have relations like this one. It is scaling, and this scaling gives the following differential constraint, or invariant solution, which is self-similar solution, or traveling wave, or something else. So there are some other solutions. So if you consider the method of degenerate hadograph, so in this case, there is a relation between dependent functions. So they are functionally dependent. In this case, for example, here we have simple wave, and as example, v is a function of u. And then it is, after that, we need to analyze this system for compatibility. And this analysis of compatibility leads us to the following relation. And finally, it gives, so if you take plus or minus, it will give you wave which is moving to right or to left side. So in method of differential constraints, so it's possible to consider as generalization of this relation, where we include also derivatives in this. So then after that, after what we assume, it is it's possible to get the following differential constraint, and this differential constraint, for example, it gives one of wave. If it is minus here, then it will be another wave. So this is about in general case, so about methods. And the method of differential constraints was developed or proposed by Nikolai Nikolaevich in beginning of 60s. And this method consists of the following. Assume that we have system of equations, and then to this system of equations, we add some additional constraints. Actually, I'm sorry that if for some, I know that Russian companies, they know a lot about this, so, but some others participants, they don't know, and I will be a little bit maybe boring. So we have system of equations, and then it is an additional system of differential constraints. Then this system it becomes overdetermined, and it is necessary to analyze compatibility of this system of equations. Actually, this system, this method of differential constraints, it was developed in competition between scientific competition of two great Russian mathematicians, Lev Vasilyevich Arsyanikov and Nikolai Nikolaevich Yanenko. And as a result of this competition, it was developed so-called method of differential constraints and method of partially invariant solutions. So, and one more time, so what is method of differential constraint? We have system of equations. In this system of equations, some function can be undefined, and then differential constraints. Here, x independent variable, u dependent, and p, it is a set of derivatives of dependent variables with respect to independent variables. And differential constraints. The differential constraints also can be, some functions can be given, some functions can be undefined. And then solution is defined by these differential constraints, is called solution, which is characterized by differential constraint. And after this type of equations is assumed, then it is necessary to apply compatibility theory for system 1, 2. And if we just require that only compatibility of this system, then this method can include all possible solutions. So all possible solutions can be described by some differential constraint. But in order to construct solutions by using this method, to find new solutions, it will be very complicated because compatibility is too general property. Then it was restricted by considering systems which are involutive. Involutive, it means that this system does not produce new equations of the same order. So system is like a complete system in case if you have one dependent variable and linear system of equations. So with one dependent variable. So then system becomes not active. And in this case, so even this condition, it was sufficient to include such kind of solutions like invariant solutions or solutions which are constructed by Lie-Backlund symmetries and non-classical weak solutions and etc. Actually, here I want to also say that in this seminar also it was methods of B symmetries which were developed by Professor Oleg Viktorovich Koptsov, so our head of this seminar. Here are some references about method of differential constraints. This is in Russian and also in my book, which was published in 2005. So now I want to say about generalized simple waves. So by using method of differential constraints, actually, if you have a system of, for example, hyperbolic system of equations, here U, it is a vector and matrix A, and this assumes that system has the following form. In, for example, it is homogeneous because simple waves are constructed only for homogeneous system of equations. Then if it is because it is hyperbolic, then it can be decomposed matrix in the following product, where lambda capital is a diagonal matrix. And then system can be written in this form. And what is simple wave? Simple wave can be described by the following. This is dependent functions are dependent on one dependent variable. So for example, here U is a function of rho. Rho, it is not vector, it is only one function. And it from method of differential constraints, it's possible to show that this corresponds to the following. It is the following differential constraint. Here, actually, matrix B1 consists of 0 and 1. It only meaning that from matrix L to choose m minus 1 rows from this matrix. So this means that just the number of differential constraints, it will be m minus 1 differential constraints. So here I want to say that simple wave, it is when right side is 0, and generalized simple wave, it is when right side is not 0. So it is assumption, this means that this is some function depending on dependent variables and independent variables, for example. So this is, so here I will talk about such kind of solutions concerning several models. So first I want to say about gas dynamics, one-dimensional gas dynamics equations.
Владик,
So then, hello? Some questions? Oh, okay, I will continue.
Сережа, извини, можно спросить, а пси
Да,
от каких
конечно.
аргументов зависит? Пси.
Вот, Саша, что аргументов зависит? Что?
Функция пси на предыдущей странице. На предыдущей.
This is here we consider first order differential constraints. So L, it is, you can see it is depends on dependent variables. It can also depend on independent variables, no problem. And function psi right side, it depends on dependent variables, independent variables. So today I will talk about some differential constraints such that includes independent variables. It became very important for systems written in invariants, Riemann invariants. Any more questions? Okay, I will continue. So in this case, if you consider one-dimensional gas dynamics equations, in particular, it is considered polytropic gas. So I want to say that first application of method of differential constraint to gas dynamic equations, it was in paper of Raspopov, Shapir, Finenko in 1977. So then it was considered one differential constraints, two differential constraints, and three differential constraints. So and it was mentioned, later I will mention about this. So then system can be, of course, written in this form. This is matrix L, lambda, and Riemann wave. For Riemann wave, we have the differential constraints are the following. So it means that if you consider Riemann wave from one point of view, so if you consider in this form, or from method of differential constraints, you can study this by using differential constraints between dependent variables and independent variables. Here, I forgot to say, U is velocity, rho is density, P is pressure, and gamma, it is polytropic exponent. So then we proved the following theorem that generalized simple waves, they can be in the following form. Actually, before it was obtained by Raspopov, Shapir, Vinenko for gamma equal to 3, and if it is gamma not equal to 3, a more general case, so it is for psi is not equal to 0. But if psi is not equal to 0, then solutions are non-isentropic. And here it is given these relations. Actually, it is interesting, the following story about simple wave, generalized simple wave, is that solution can be constructed by integrating with respect to along characteristic. So this
Владик,
is...
посмотри, ты еще не обулся?
Sorry.
Выключи микрофон.
I have shoes on me already. So, and for example, for reaffection waves, which are very well known, for example, for Gursa problem, when it is given characteristic and given data on characteristic, and at some point of this characteristic is degenerate, and so singular, and in this singular point it is considered PU diagram, and this PU diagram can be constructed by the following way. So then Xi, it is just considered relations, how characteristic is coming from this singular point. I am sorry. And for such kind of generalized simple wave, conditions are absolutely the same in this singular point. So PU diagram is similar, absolutely not similar, even the same. So But in this case, such kind of solutions will be non-isentropic, so rarefaction waves. And for example, we considered this is like only just to imagine, it's not correct. So we have two pistons, for example, and they are moving, and then here it will be some waves, and assume that they are non-original. It was not from a state condition, it was some non-homogeneous conditions inside. So then it will be some shock waves. And it's possible to construct the following that assumes that we have two generalized simple waves from one side of shock wave and from another side of shock wave. Then it's possible to reconstruct such kind of solution by just using one data at one point. And at one, we have this data, then we can construct solution on shock wave, and then using data on shock wave, using characteristics, along characteristics, we can reconstruct solutions. So this was done by, so this one, it is possible to see that this is integration, so it is interaction of two rarefaction wave. And actually here I want to also, I forgot to say before that I told about scientific competition, and so between Nikolai Nikolaevich and Lev Vasilievich Ovsyannikov, and usually it was question for students from one side, which gives seminar in another side. So usual question, can you do by my method? So can you construct, for example, solutions which are partially invariant solutions, and can you construct them using method of differential constraints, and quite opposite. So then I want to say that here on this type of solution, it's possible to answer that yes, some of solutions we can describe by both methods. For example, this solutions that we described here, they can be also obtained as a partially invariant solutions, but in prolonged space. So it is more complicated than, I think, than using method of differential constraints. So now I want to say about the following, that the next application that I will talk about, it is systems written in Riemann invariants. So here we studied with Natalia Manganaro in 2002, we published the following, that if we have differential constraints of the following form, then here I want to mention that it is not involves independent variables. So then we analyzed and it was constructed several applications actually, but I will talk about the following, that how it is important to include independent variables in differential constraints. So an example, it will be given by the following homogeneous system. For simplicity, it will be homogeneous system of equations. So if we consider these differential constraints and this system of equations, so then conditions for system to be involutive, we have the following conditions. So if we assume that here are no independent variables, so then in case of if lambda r, this is partial derivative with respect to r, not equal to 0, so then immediately we have that only simple waves are solutions of this overdetermined system. Actually, it is not enough. So then it was idea that what happens if we include such independent variables. So then in this case, now I will talk about the following problem. So we have a homogeneous system of equations written in invariant Riemann invariants, and we have the following differential constraints. So here P is not equal to 0, because if P is equal to 0, it will be Riemann wave, and it is not interesting from this point of view. So then conditions for system to be involutive are here. So there will be the following. Actually here from consideration, we got the following case when lambda is equal to mu, because if lambda is equal to mu, so it gives just a simple wave, and so another degenerate case if lambda s is equal to 0, because s disappears from here, it will be equation including only r. Then for non-degenerated case, it's possible to show that general solution of this system of equations, it becomes like the following, not like it becomes this one. Here, T naught and X naught, it is some arbitrary constants. I included them in order to consider later Cauchy problem. So they are included for later consider Cauchy problem. So the function g, which is involved here, it is defined by coefficients lambda and mu. So this is completely defined. And the function h, which is here, this is it's necessary to solve this ordinary differential equation because r here not involved, and so it is located in parameters lambda and mu. So then and in case if function g, it is the following function, this one, if it is not equal to 0, for most applications, it is not equal to 0. Then in this case, it is interesting that it's possible to write this system, this differential constraints, I mean the right side of differential constraints in the following form. Here, if R is completely defined by lambda and mu, and HR is arbitrary function. Application, because of this arbitrariness, we can construct a solution of any Cauchy problem. So actually any, of course, it is in quotations because some Cauchy problem, actually this theory is local. So then in this sense, it is any. So for example, if it is given initial data, so this is initial data, and assume that it is possible to solve this initial data with respect to x. So for example, we can write that xi it is initial data for t is equal to t naught. So then if it's possible to solve using inverse function theorem, for example, so then we have the following function, and this is in order to say that this is inverse function to r naught x, and then h is given directly, so through initial data. And in this case, we have initial data, we have a system of ordinary differential equations, we have here this function also, all functions are defined, so then by this way it's possible to construct any solution of any Cauchy problem. So then here it is one of examples, for example, one-dimensional gas dynamic equations. So here V is velocity, rho is density. So this is C, it is sound speed, and the relations between C and phi, it is the following. So then it's possible to show that general solution of compatibility conditions that I wrote before, so they will be in the following cases. So because solution was a second order equation, and actually it has 3 arbitrary constants. So then here solutions depends on these constants, and this is case A, B, C, and D. And I want to say that in these cases, actually, there are 3 constants. So we have this constant Q, Q naught, and X, K. And also integration for function phi, I'm sorry, integration for function phi, it also gives additional constants. So then we can approximate state equation by this type of solutions. So I want to say that this is just general in case, and if you consider local solutions, then it's possible to consider this as approximation of some data, experimental data. So another case that I will demonstrate, it is case of nonlinear elastic material. So here sigma, it is stress, epsilon deformation. This is state equation, relation between deformation and stress. And this is equation, one-dimensional equations describing nonlinear elastic material. So then if we introduce function phi small that by this way, So then it's possible to rewrite this system in Riemann invariants, where lambda is the following representations. And of course, a lambda s here not equal to 0, because if lambda s is equal to 0, then this corresponds to linear case, so linear material, linear elastic material. Then, as I told, that it's possible to solve conditions for such kind of system for involutive conditions. So then it is the following. First, we solve this one G in the following case, and then for phi we have the following equation, the following ordinary differential equation, and solving this, we can say also, we can find also 4 cases. Here I will demonstrate for last one, I will demonstrate, so this is, we consider the following case. So here function psi and function phi is reconstructed also. And for example, let us consider that initial data for epsilon is constant, so deformation is constant, and are not, for example, it will be linear function. Actually, in this case, we have all functions involving in system of ordinary differential equations along characteristic. And it's possible to show that in this case, this is derivative of epsilon. These derivatives are along characteristic. It is not partial derivative t. So then it's possible to show that all these derivatives are equal to 0 starting from n is equal to 2. So then this means that epsilon is a linear function with respect to t. And this gives immediately trivial type of solution when epsilon is a linear function with respect to t and velocity is linear function with respect to x. So this means that this is not interesting case from applications point of view. Now I considered some another case, logarithm I just take in order to easy find inverse function. And so in this case, function h, it will be the following function for this initial conditions, function h, it will be the following. And then initial conditions which are defined. Now we can use method of characteristics, integrating along characteristics. And it was done by numerically using Runge-Kutta 6-order numerical scheme. So we can reconstruct, for example, here it is velocity, here it is deformation. Actually, this velocity and deformation are given in xi t variables. So in xt, we have to reconstruct them, and so not so simple. And here, this is how distribution of velocity at different time of moment of time. And this is a different deformation, distribution of deformation at different type or different time t. Then here, as I told that it's necessary to reconstruct in variables xt, so this is reconstruction. So, and it was used here, spline approximation for reconstruction. And so then this is state equation that you can see that it is not straight line. If it is straight line, it will be linear. But this is not straight line. It's possible to also reconstruct this type of solution. Next topic that I want to talk about magneto-gas dynamics. So, for example,
Это я
questions?
много раз. Тут что-то, ну вы там где-то активировали, куда-то зашли на другое, просто посмотреть. Спасибо.
Sorry, so okay, I will continue. So magneto-gas dynamics in three-dimensional case, it can be written in the following form. So here rho is density, u is three-dimensional velocity, p is pressure, b it is magnetic induction, and gamma it is a polytropic exponent. So here this is total material derivative, and as I told that this is a vector and this is also a vector. So, and I will consider one-dimensional case. So in one-dimensional case, equations reduced to the following system of equations. Actually here, B1 becomes first component of magnetic induction becomes constant. And so I considered case when B1 was equal to 0 for simplicity. And so matrix in this case, matrix form, it can be written in like this one. So here matrix A also can be reconstructed. Lambda, it is the following diagonal matrix. So and then it's possible to use method that I explained before. So before this, I want to give some remarks for first remarks that actually it's possible to see that row B2 and B3 are functionally dependent. So for example, if B3 is a function of row and B2, it's possible to reduce this equation to this form. And second remark is concerning that if rank of the following Jacobi matrix is equal to 1, for example, B2 is a function of row and B3 is a function of row, it reduces to so-called to gas dynamic equations, but with so-called Mi-Grunizen state equation. Actually, I heard about this state equation recently from Sergei Gavriluk. So. And it is interesting that also in magnetic gas dynamics, it has also application. Then in this case, if you consider differential constraints, as I explained before, it must be related with matrix L. They will have the following form. And functions phi, right side, is we need to find using conditions for system to be involutive. And in this also, solution can be reconstructed from initial data along a single characteristic system of, so this is characteristic conditions along single characteristic. Actually, I'm talking about here sound characteristic. If B1 is not equal to 0, then it's possible to construct, I think, it's not done, but I think that it's possible to construct so-called Alfenius waves. So here Alfenius waves are cut. So because B1, we assume that is equal to 0. And question is, what about compatibility conditions? Actually, not compatibility, involutiveness conditions. So it's possible to show that there are two different cases. So one case when right side has the following form. So here for function phi1 tilde, it is arbitrary, but function m can be reconstructed from the following partial differential equation. And this partial differential equation question is maybe there are some solutions. Actually, there are two trivial in case that trivial is easy to solve. So this is one case. In this case, function h is arbitrary. Actually, this expression, it becomes integral along characteristic. So it is not changeable. And another case when function phi1 is equal to 0. So then in this case, it's possible to construct even more integrals along characteristic. And here it is 5. And only one equation you need to solve along characteristic.
Serежа, we must reload Zoom.
Okay. I want to say that now it's because 40 minutes passed already, so we need to reload Zoom and use the same strategy when you applied first time.
1 minute.
Do I need to stop or continue?
Stop, please.
Okay. So see you in a few minutes.
Yeah.